All right, welcome back. Let's continue our very fruitful discussion. So in this session, we're going to have two papers, and then John will discuss both papers. So let's first welcome Adrian Lam from Imperial College to talk about the economic costs of climate change. You have 30 minutes.
All right, thank you, Dawn. I would like to thank the organizers for accepting this paper, as well as for you guys to attend this session. So I'm super excited to talk about our paper, The Economic Costs of Climate Change. So this is a joint work with Claudia Custodio at Imperial, Miguel Ferreira at Nova, and Emilia Garcia Ependini at Zurich. So let me start with the motivation. So it is generally agreed that global average temperature will likely increase by at least 2 degrees Celsius relative to pre-industrial levels by mid to late 21st century. And the number of occurrences of extreme weather events are also likely to increase. So associated with this is that there can be a lot of potentially devastating social and economic outcomes. Now, the effect of changes in climate on economic outcomes are not just long-term. So there are a number of studies that find higher local temperatures affect short to medium-term economic outcomes, such as agricultural activity, farmland value, worker injuries, and total factor productivity. So I think that the last 2 points are very interesting in the sense that if we find local temperature affecting establishment level productivity, then without any friction, it should just aggregate up and it should affect firm sales. But it seems like this isn't the case. So the evidence on temperature affecting aggregate firm sales is actually mixed. So in this paper, the research question that we have in mind is, how do changes in temperature affect firm sales? Now, we think it is not super easy to do this empirically because first, sales is determined by supply and demand. It is unlike agricultural outcomes such as crop yield. Then temperature may also affect both the supply and demand for a firm's product. So what we are going to do in this paper is that we use production networks as a laboratory. So essentially, we are looking at the supply chain, we are looking at interfirm sales, and we use an identification strategy comprising of 3 elements. So first, we argue that changes in temperature are exogenous to individual firms' activities, at least over the short horizon. Then, well, because suppliers are located in different locations, they are differentially exposed to changes in temperature. So what we are going to do is that we will compare changes in sales of suppliers to the same client in the same year as an attempt to control for client year-specific demand shocks. So let me walk you through this in a graphical manner just to highlight the intuition of our estimator. So let's just focus on one client, client J. So in 1 year, client J has a total demand for intermediate goods. And conditional on this demand for intermediate goods, client J buys from 3 suppliers located in different locations. Now suppose that supplier 3 experiences a hot year, and we also find that the sales from supplier 3 to client J decreases. Now suppose we find this relationship appearing systematically across many client-supplier pairs, then we can possibly argue that it's really the changes in local temperature affecting the changes in interfirm sales conditioning on the demand by a client in a year. Now, so put this intuition into an empirical specification, what we have is the following regression model. So the dependent variable is the change in log pair level sales. So what we are looking at is really the sales from supplier I to client J in year T. The key independent variable is this change in temperature. So we're looking at the time series change of the temperature in a location of the supplier. Then for some specifications, we also control for average precipitation because weather variables can be correlated. And we have some firm financial controls that are lagged. And what is most important is this delta JT, which is a client year fixed effect. So the idea is we're trying to absorb the client time level demand shocks, and we try to compare the differential changes of temperature on the pair level sales. Now, the inclusion of this client time fixed effect requires us to look at client-supplier pairs where a single client purchases from multiple suppliers. So it's really a differential estimator that we are looking at here. So let's have a very high-level overview of the results. We find that a 1 degree Celsius increase in average daily temperature leads to a 1.2% to 1.9% reduction in interfirm sales. We explored the heterogeneity, trying to understand the economic mechanisms behind, and we find that there are 3 mechanisms. First, we find that labor supply and productivity seems to be a channel because it's consistent with prior literature. Then we also find that financial constraints and adaptability plays a role. So if firms doesn't have the capacity to adapt or to mitigate this weather shocks, then this will show up in their sales. Then we also find switching costs to play a role in understanding our findings. Then we also find that extreme heat and extreme cold events have a larger negative impact, ranging from 6 to 8% for extreme heat and somewhere in the magnitude of 30% for extreme cold events. So these are massive. So the way we think of how this paper relates to the literature is that there are a number of papers finding heat or temperature reducing productivity and or firm performance. So basically, the paper by Grafstein and Kahn, as well as Chen et al., find that local temperature affects establishment level productivity. Colmer, Martin et al., they find that temperature affects value added and lock employment, but not really a lot on productivity. Then there's also this paper by Nora, and I'll just not spoil her results here because she's presenting it next. Now, so what is super interesting to us is that there's this RFS paper by Adom et al. That find temperature has no effect on sales, productivity, or profitability. So we kind of see mixed evidence here. So in this paper, what we are going to do is that we provide an estimate of the impact of local temperature on firm supply, controlling for demand shocks. And we think this is very important in highlighting how temperature will affect firm cash flows, because by really understanding this, we can really think about policy and think about what kind of incentives shapes firms' decision in incorporating measures to mitigate exposure to climate change risks. Now then, let's go into the data. So we use CompuStat segments for the supply chain data. So it's a data set comprising of client-supplier pairs in the United States in between year 2000 and 2015. So these are main clients. Suppliers have to disclose these kind of main clients, which is defined as if these clients contribute to more than 10% of sales of the suppliers, then they have to disclose these clients. Now we have this name matching algorithm that we hand match the pairs. And we find that these are essentially main clients because the purchases from them represent more than 30% of suppliers' total sales. Now for the weather data, we use Prism Climate Group for daily weather variables, which are super fine, super granular. So this is a gridded weather product data at the 4 times 4 kilometer grid in continental United States. So essentially what the climate scientists here do is that they interpolate these weather variables from nearby weather stations with state-of-the-art climate engineering controls. So these are smooth and scientifically valid estimates. Then we obtain extreme weather events data from the NOAA storm events database. We aggregate these weather variables to the headquarter county level and adjusting for fiscal year months effects. So in the end, we have this sample. The unit of analysis is at the supplier client year level. We have more than 12,000 observations, of which there are more than 1,800 unique suppliers, 400 unique clients, on average 700 observations per year, and 5 suppliers per client per year on average. And this is key because our identification strategy really requires on a client buying from multiple suppliers. So some key summary statistics. So we are looking at the change in log sales at the pair level. So the mean is positive with quite a bit of dispersion here. So since we are aggregating weather variables in a year, the average temperature, the level of it, is around 13.7 degrees Celsius. Again, there is also quite a bit of dispersion, and this is an annual average. So we're averaging in a year, so that's why we have this figure here. The key independent variable is the change in temperature. So as expected, it's very close to close to zero in the mean. But what is remarkable is that this change in local temperature has a large dispersion. The standard deviation is almost 0.9 degrees Celsius. Then we also have some extreme cold events and extreme heat events. And these are really extreme events. They are very rare in the sample, but then we have also included them just to try to see if we can see some consistent results to our hypotheses. So here are the baseline results. So in columns 1 to 3, we do not control for precipitation, and in columns 4 to 6, we control for precipitation. So across columns, we have different fixed effects trying to absorb the type of unobserved heterogeneity at the corresponding level. And because weather variables are spatially correlated, so we are clustering at the county level. So what we find is that the coefficient of the change in temperature variable is statistically significant, and economically it's also quite meaningful, because what it implies is that a 1 degree Celsius increase in local temperature leads to a 1.2% to 1.9% reduction in interfirm sales. Now remember, the dispersion of this change in temperature is around 0.9 degrees, so we think that this is actually something that is happening quite frequently. So I think the baseline results suggest that after controlling for total demand of intermediate goods by a client in a year, we find that local temperature shocks will lead to a reduction in interfirm sales by the suppliers. Next, we want to understand the economic mechanisms behind, and we have 3 major channels in mind. First, we have this labor supply and productivity channel. So the idea behind this is really consistent with the prior literature, which shows that local temperature affects establishment level total factor productivity and worker productivity, and it reduces labor supply. The hypothesis we have in mind is that we expect the negative effect of temperature to be more pronounced for labor-intensive or heat-sensitive firms. So we do this by doing a set of heterogeneity analysis using some proxies for labor supply and productivity. In the first 2 columns, we split the sample by whether the firm is in manufacturing industries or not. So the idea is that manufacturing industries are more labor-intensive, they rely on more worker productivity. And in that case, we should expect firms in manufacturing industries to be driving our results, which is the case, and the managers is slightly higher than our baseline estimate. Whereas if we look at non-manufacturing industries, there really isn't much going on there. Then in a similar spirit, we split the sample by whether these firms are in heat-sensitive industries or not in heat-sensitive industries. So heat-sensitive industries are really industries where the major economic activities are taking place outdoor. So the workers are there, they have to subject to these changes in temperature because they're working outdoor, and in that sense, they are more heat sensitive. So we do expect heat sensitive firms to be more affected by local weather shocks, and this is also what we find. The magnitude is also quite consistent with the manufacturing industry's results, and we also don't find much going on for non-heat sensitive firms. Then the third analysis is to split by this labor intensity variable defined as number of employees divided by total assets. So the idea is that if the employee to asset ratio is higher, then you really is a more labor intense firm. And in this regard, we do expect firms with higher labor intensity or higher employee to asset ratio to be driving the results. So here we split the sample by the mean value. And again, consistent with our conjecture, is the high labor intensity firms driving our results, whereas there's not really much going on for low labor intensity firms. So together, we think this set of results highlight a labor supply and productivity channel, whereas it is the temperature affecting worker productivity. That's why we see a result in inter-firm sales. Then the second mechanism is the financial constraints and adaptability channel, which I really like. So the idea behind this is, suppose I'm a firm. If I do not have the capacity to adapt, say if I'm financially constrained, or if I don't have the operating flexibility, then subject to this shock, I can't do any things to mitigate the change. But if I have the resources, then maybe I can increase the amount of temporary workers so that I can just boost my total output level. Then I would not be that affected. So the hypothesis here is that we expect the negative effect of temperature to be more pronounced for firms with financial constraints and for firms with lower operating flexibility. So we do this analysis in two panels. The first panel are measures for financial constraints, and the second panel are measures for operating flexibility. So the first split is really to split by the proportion of long-term debt maturing in the coming year. So this variable is saying how much of my long-term debt will mature in the coming year. So when it matures in the coming year, then as a firm, I will have to reserve some liquidity to pay off the principal and interest, and this lowers my financial flexibility. So in this regard, we do expect firms with a higher proportion of long-term debt maturing to be driving the results because they just can't adapt to this productivity shock. And consistent with this conjecture, we do find this result, and the magnitude is actually very strong. It's 2 to 3 times of the baseline estimate. Then when we look at firms that are less financially constrained or with higher financial flexibility, the results are really not there. Then we repeat the exercise. This time we use a easier to understand measure, which is whether a firm receives a credit rating by a credit rating agency. So if they are non-rated, then they are more financially constrained and they just can't use short-term funding to mitigate, to say increase the number of temporary employees. So what we expect is that non-rated firms should be driving the results, and this is also what we find. And we do not find much effects going on for firms that are not really financially constrained. So let's move on to operating flexibility. So the first measure we have in mind is firm size, because the larger the firm it is, we should expect they have more resources. So we expect firms with lower total assets to be driving the results, whereas firms with higher assets to be less affected. And this is also what we find. And again, the magnitude is really high. It's 2 to 3 times of the baseline estimate. So the second measure for this operating flexibility is whether a firm has just a single business segment or is a conglomerate. So the idea behind here is that we want to explore the role of internal capital markets. If a firm have multiple segments, then they have an internal capital market, and they can just pull resources from less affected segments to more affected segments as a way to adapt to the productivity shock. In other words, we expect that firms without an internal capital market, they are less operationally flexible, then they will be driving the results and the reduction in firm sales. And this is also what we find. So together, we argue that this set of results highlight that the role of financial constraints and adaptability is very important in understanding these results, and the capacity to adapt is really something that that highlights whether there is an impact of local temperature on inter-firm sales. Then the third mechanism we have in mind is the switching cost story. So the idea is that if the So suppose I'm a supplier, I get shocked, and then I just can't produce as much. Then if my client can easily switch away from another supplier, then my reduction in productivity will have an amplified effect on interfirm sales. So the hypothesis we have in mind is that the negative effect of temperature to be more pronounced for firms selling standardized goods and for client-supplier pairs with weaker relationships. So we have some measures that proxy for high and low switching costs. The first one is whether a firm sells standardized goods. So while we find that the coefficient of the change in temperature variable are both negative and statistically significant in these two subsamples, we do find that firms selling standardized goods to have a larger size of the coefficient, which is consistent with the switching cost story, because when you're selling standardized goods, then clients are easier to switch to another supplier. Now, to capture this product specificity idea, we split the sample using this patent measure. So the idea is that if I'm a supplier that produces highly specific goods, then I should have more patents. So if I don't have any patents, then my goods are more substitutable, it's less specific. So in this sense, we do expect firms with no patents to be driving the results, whereas firms that have patents that are selling more complicated goods should be less affected. And this is also what we find. Then third, we split the sample by the pair level distance along the mean value. So the idea is that geographical distance can noisily but proxy for business relationship. And we expect that more distantly located firm pairs means that the switching cost is lower for the client. And then it should be these firm pairs that are driving the results. And again, we do find high distance firms to be driving the reduction in firm sales. So together, we argue that this set of findings highlight that switching costs also have a role in local weather shocks affecting interfirm sales. So we have done a number of robustness tests. I'll just highlight the more interesting ones. So we have also repeated our exercise using postcode level weather variables, and that is all right. Then another hypothesis is, should we expect a linear relationship, or should we expect that local weather to affect firm sales in a quadratic manner? So to test this hypothesis, we have included quadratic weather variables, but then we find that the coefficient on the quadratic terms are insignificant, and the change in temperature variables, the coefficient magnitude as well as size does not change. So we think it's really operating in a linear manner. Then to really take into account the broader spatial correlation of weather variables, we've also clustered at state level, and that works fine. So there are some additional tests. So we have so far just been looking at this change in local temperature, which is kind of a smooth average variable. So what about extreme weather events? Also, because our key dependent variable is this change in log pair level sales, so it's really looking at the intensive margin. So what about the extensive margin? Does weather shocks break supply chain relationship in the United States per se? So let's look at extreme weather. So when we look at extreme heat events, it's very strong and statistically significant. So the coefficient of the heat event variable is negative and statistically significant across specification, and the magnitudes are high, ranging from 6.2% to 8%. So this means that if a heat event occur in that location, then firms will sell 6 to 8% less. Then when we look at extreme cold events, it's even more dramatic. So if an extreme cold event happens at a supplier location, then it leads to a 30% reduction in interfirm sales. Now, these are pretty consistent with what we would expect, but then the caveat is that these are really extreme weather events, and by looking at the summary statistics, we know they are very rare. Now then, here are some results on the extensive margin. So basically here what we want to see is whether the change in average temperature will lead to termination in supply chain relationships, and whether extreme heat and cold events will lead to termination in supply chain relationships. So in the first panel, we are looking at the change in local temperature, and we don't really find much going on, which means that changes in local temperature don't really break supply chain relationships in the United States. Then when we look at extreme weather events, we do see a lot of positive coefficients, but then they are not really statistically significant except for extreme heat in one specification. So we think that extreme weather events seems to have some impact on termination on relationship, but then this is not super robust. So perhaps something else is going on. But in short, we don't find weather shocks to have much going on, to have much impact on termination of relationships. So
you have 4 minutes.
Oh, so I'm helping. So we're good in progress. So in conclusion, we have identified the effects of local temperature on firm supply, and we think this is something that is important because we're controlling for unobserved changes in demand. We find this effect is driven by 3 economic mechanisms. One, it's labor supply and productivity. Second is financial constraints and adaptability. And third is the switching costs. We find that extreme weather events are more disruptive, but then we don't really find much going on the extensive margin. So this is basically what I have, the key results that I want to show you guys. So I thank you for your attention. I look forward to John's discussion and the Q&A, and I'm super happy to talk even after the conference. So thank you.
All right, thank you very much. The next presenter is Nora Pankratz from UCLA. And the title is Climate Change and Adaptation in Global Supply Chain Networks. You also have 30 minutes.
Yeah, thanks a lot, first of all, Dong, for the segue. Thanks to the organizers for including this paper on the program. Really excited to present this here. And last but not least, also thanks to you as the audience for tuning into this session. All right, so this is titled Climate Change and Adaptation in Global Supply Chain Networks, and it is joint work with Christoph Schiller from Arizona State University, who's also here in the chat today. And my name is Nora Pankratz, and I'm a postdoc at the University of California in Los Angeles. Let me jump right in, but I don't think I'll manage to start without a link to recent affairs. So I think the current public health crisis, and especially the beginning of it, has made it very salient to what extent there is resilience in global supply chains to unforeseen events and interruptions. And what we do in this paper is to try and better understand both supply chain resilience and responses in supply chains to another looming threat. And that threat is climate change. So if we look into this from an industry point of view, and especially when we set out working on this paper, we started just looking around whether there was any evidence of this mattering to practitioners. And somehow it seems that practitioners were a little bit ahead of the academic community in this sense. So first of all, already in 2015, there was a survey by PwC that said that 50% of CEOs really named climate change, and not just climate change in general, but specifically climate change in the context of supply chains as a primary concern and one of their primary concerns. Moreover, it was also obvious that that was already a topic that a lot of supply chain consultancies were busy with, but also insurance companies stressed as a potential topic and a potential challenge in the future to manage these skyrocketing expenses that are expected from increases in these distortions to supply chains. So what we then try to do is, sorry, I'm just going the wrong direction here. Okay, I'll do this way. So what we then tried to do is link that to the academic literature that was out there so far, and we set up our research questions in this way, broadly relating this to 3 different strands of literature that were already existing. So first of all, while there wasn't much evidence, actually hardly evidence at all, on the indirect effects of climate shocks to firms and financial performance, there was this fast-growing literature, I think largely also fostered by the RFS call on climate change and finance, that investigated to what extent firms are directly affected by these hazards. And I think also Adrian's really nice presentation links into that. But so there were already studies out there on, for example, the effect of temperatures on firm performance, both in economics and in finance. Moreover, we found that there was a broad literature generally on the propagation of any type of shock in supply chains. And particularly one paper that we refer to a lot, that's a really nice study in the QJE by Barou and Sauvagnat from 2016, that was studying the propagation of natural disaster shocks in supply chains. And so in that sense, the first step of our study, or the ambition for the study, was to put these two things together and look into how climate-related shocks that maybe might not make the news as a natural disaster propagate in supply chains, and whether we find evidence for a financial propagation, so to say. Okay, but then potentially even more importantly, and I think very much the focus of this paper, both in the version that is currently out, but also in terms of an update that we're currently completing, is related to another strand of literature. And that is something that has been predominantly developed in environmental economics. And I started off here with a really broad question. That would be the question of how do economic agents actually learn about climate change and how do they respond? And putting this into the firm, finance, and supply chain context, that essentially means, okay, so if we see this propagation of shocks, as financial economists, we might expect that firms respond in some way. And so that's something that we try to better understand here, to what extent there are responses in the formation of supply chain networks, if there's any chance in underlying climate risk exposure. And with that, let me take to the actual research questions, as well as the spoiler of the results that we're going to go through in the next 25 minutes, I guess. So again, we have these broad two questions that will be the guiding questions of this presentation. So first of all, do we find evidence that climate change related shocks propagate in supply chains? And then second, if we take that as a potential financial incentives of firms to do something about that, what do we see? Do we see that firms adjust their supply chain networks when shocks become more frequent? Or is there, say, not enough evidence for something like that happening at the moment, potentially given the extent to which changes in the climate have already been realized? In short, what we find is the following. So first of all, we find that both floods and heat waves, so those are the two types of shocks that we decided to study here, affect both directly suppliers' financial performance, as well as the performance of a customer that's located remotely in a different location. And we find that this propagation is kind of substantial if we compare both this direct and this indirect effect. For heat, the propagation is smaller, so only 10% of the initial effect are passed through from the supplier to the downstream customer. And for floods, that's a little bit more, or a larger effect, close to 30%. Moreover, we then go away from, say, these estimated short-run elasticities and think about, okay, what happens if there's a change in the perceived distribution of climate shocks? And the main result to stress here is that we find, if we investigate the supplier locations and we compare the number of realized flood days or heat days at the location of the supplier, not by itself, but compared to a benchmark of what could have been expected by the customer firm in the beginning of the supply chain relationship, we find that it becomes more likely that customers end these supply chain relationships. And again, so to say, in a proportion that holds or is in line with our estimations on the first stage of the study. So we find that for heat, customers become 11% more likely. And for flooding incidents, customers become 23% more likely, compared to the baseline probability to replace their suppliers once there is this difference between their experience with climate shocks and what they could have expected at the beginning of the supply chain relationship. We have one more piece of evidence on that note. So actually this data set also allows us to identify not only the terminated supplier, but also the potential or very likely replacement of this initial supplier. And then what we do is we compare the exposure to climate risk of this initial supplier as well as the replacement. And we find that it looks like there's a higher probability that once a supplier gets terminated for reasons related to changes in climate risk, it becomes more likely that the new supplier is less exposed to climate risk. Yeah, and so while this is the wrap, so to say, of the main results in our study, I think one thing or one theme that is important to go into is, again, this broader topic of learning about climate change and how firms make decisions related to climate risk. And the really interesting thing that we find here in this context is that while these two results might suggest that firms are really aware of climate change and consciously manage that, we find quite strong evidence that they actually do that, just learning on their experience with climate shocks, and to some extent ignoring what's out there in terms of information and projections of actual change in the future. And I hope I'll get to that later on, so more of that later in the talk. All right, so with that, I hope I've given you a good sense of direction in this presentation. Let me quickly walk you through the main components of the data that we compiled to make all of this possible. So essentially, there are three really important components. The first one is probably unsurprisingly the data on supply chain relations. So the data set that we use here is FactSet. So that's a global data set on relations between customers and suppliers. And it should comprise the public disclosure, for example, 10Ks in the US on the existence of these relationships. However, on top of that, FactSet analysts also collect data from other sources. So for example, other firm-specific reporting, news, and so on and so forth. And in total, we observed something like 25,000 pairs between customer and supplier pairs in this data set. And then what I would want to draw your attention to next is this map here, which shows you the distribution of these suppliers. So first, I think this is nice to look at just to illustrate that this is truly a global data set. But then second, it's also a really nice segue to one of the main challenges in not only this paper, but this literature in general. And that is related to the measurement of firm locations and the connection to physical climate risk. So what I mean by that is the following. Here, what you see plotted in this picture is actually the headquarter locations of these firms. Of course, headquarter locations, there might be a gap between that location and the main location where firms operate. And we really have to make sure that we come up with a reasonable link between the physical risk and the location in order not to unnecessarily bias our estimates or get noisy estimates here. So I think there are two things to be said about that. I mean, first of all, you can think about the ideal solution to that problem or the ideal scenario. And I think that scenario would be that we would have information at hand on all of the firm locations, but not only that, but also data on how we should think about the weighting of these locations, how they relate to each other, so that we could come up with a sophisticated way to really measure the weighted exposure to climate risks. However, especially in this global context, this is extremely difficult. So what we can do here as the next best solution, and which is also the approach that we're taking to solving this problem, is we collect all data we can find on the location of establishments, subsidiaries that are fully incorporated, branches, all types of locations that we could think of. And in total, that's a number of 1.1 million for all of these, I think a little less than 8,000 supplier firms in our sample. And what we then do with that is we create a measure how many of the facilities per firm are located within a radius of 30 kilometers of the headquarters. And then we use that measure to at least exclude data points from our sample where we can say, okay, if there's less than 1 in 10 facilities or establishments from locations within this radius, then we decide to exclude this observation just to make sure that we don't unnecessarily increase the noise in the sample by including data points where we actually have very little control over where operations actually take place. All right, so that much to be said about the distribution, although maybe I want to add a note just because that's a question that also comes up very frequently. So of course, we're mindful that there's a lot of heterogeneity in these relationships in terms of the industries. I think we have a focus in this data set on manufacturing firms, roughly 2/3 and 1/3 in services. We explicitly exclude financial services just because we thought in that sense it's very unclear what the traded good would be. For the rest of the presentation today, I'll present you the average result across all of the industries that we retain in the sample. However, again, just to stress that of course these heterogeneities matter, and especially in a new version of the paper, we try to also incorporate that in a meaningful way to illustrate how this might differ based on the industry a firm operates in. All right, but with that, on to the next really important data block here, and that is the exposure to climate risk and how we want to measure that. Yeah, so first of all, again, so we decided to study 2 different types of shocks here. First of all, heat and then inundation. We will be a little bit less focused on what the exact channel is through which these matter, but just again, as a so to say, quick summary of the literature. So for example, for heat, there are some productivity effects at the firm level documented related to heat, definitely with large standard errors, but there are a couple of papers in this literature that indicate that that is something that is to be expected on average. Moreover, there's a micro literature on, for example, the risk of injuries at the workplace, as well as traffic accidents under heat, and that there's a positive relationship between temperatures and such risks. And moreover, for example, also in Europe, it might be interesting to think about other transportation channels. So since often heat is correlated with drought, there are effects, negative effects on transportation, just if river levels drop too low. And in that sense, the transport of goods has to be kept, thinking about everything related to transportation on waterways. For inundations, I think the channels are a little bit less debatable. So water in your facilities is probably not helpful for production. But again, there might also be second order effects here, something like infrastructure that is affected or affects how workers can get to work. Okay, and how we measure that is indicated below. So first of all, for this global data, we use the ERA5 data set. That's a 30 times 30 kilometer roughly grid of daily maximum temperatures. We choose to focus on the daily extremes just because those are indicated to be most important for productivity effects. And there are lots of different definitions possible. So we work both with absolute and relative thresholds in the new version of the paper. However, our main measure here is the number of days during a financial quarter during which the firm was affected by temperatures over 30 degrees. Moreover, for floods, we use data from the Dartmouth Flood Observatory. So that's a combined data set on hand-drawn polygons of areas that have been affected by floods, as well as remote sensing sources. And how we use that data essentially is to create an overlap between the location of firm assets and these floodings to create an indicator whether firm operations may have been affected by these incidents. And then finally, a new addition to the data set is that we also incorporate projections. So we go with the CMIP5. That's the data corresponding to the last IPCC report and mainly focus on the business as usual scenario for mid-century. And for now, we mainly go with the models of the Max Planck Institute. But on that note, I think it's most helpful if I explain later on, once we get there, how we incorporate this data. All right, I have to go back one slide once again. So what I've shown you now is, first of all, the data on supply chains. Second, the data that we have at hand on climate risk exposure. I think in the beginning, I announced 3 different components. So the third component does not have a dedicated slide here. And that's essentially referring to the financial performance data that we need. What we use here is the world scope data set, which is also a deviation from our initial version where we use the CompuStat data, just because in writing this first version of the paper, that was a little bit more convenient. But we then found that world scope would give us or triple the size of the data set at hand. And we were really comforted, or so to say, it gave us a lot of confidence to see that the results really hold and stayed very similar across both these data sources. All right. But I think that was complete. So those are the 3 main data components that we need. And with that, let me take you to the estimations and methodology, or the other way around, methodology and estimations. So first of all, what you see here is basically the baseline of the study and just this motivating stage of asking the question, do the shocks or the financial shocks related to heat waves and floods in terms of heat days and flood days, do they propagate in supply chain networks? And the methodology we use here is fairly standard. So on our left-hand side, we have the performance of a customer firm that is not located in the same place as the supplier. So we make sure that that is the case by imposing a geographical distance between the two. And then we test whether climate shocks, as well as 3 legs of these climate shocks, quarterly lags, whether those have an effect on the performance of the remotely located customer. And on top of that, we control for a couple of potentially confounding economic trends. So what you see here is, for example, trends over time by industry, trends over time by types of firms, as well as a location-specific fixed effect that just leads to us analyzing only the random variation around a location-specific average, which is really important here for the identification because, of course, we observe all kinds of places around the world, and there might be a confounding correlation with purely cross-sectional correlation with temperatures and locations. So here we focus on the within variation only. Okay, and with that, so basically what we do is we implement this methodology, and what I'm showing you now is the result of doing that. So we find, in short, that both heat days and flood days negatively affect the financial performance downstream in supply chains. And what I decided to show you here is just the picture for heat days. So we find that this effect sets in with a little bit of a lag of a quarter, but then both revenue over assets and operating income over assets are slightly negatively affected by these shocks to the supplier firm. And again, we ensure that there's a physical distance between the two, as well as calculate the difference between these indirect and direct effects. If we compare the direct shock to the supplier and the shock, what you see here, indirectly to the customer firm. Two other things to highlight about this would be the following. First of all, if we look into flood days, this effect is much stronger. So this also, again, gives us some confidence that what we're estimating here makes sense. So the size of the effect in flood days is at least 5 times as large. Moreover, maybe it's important to highlight that what matters here for the rest of our study is maybe even less the financial magnitude of this, which is substantial, but not the determinant, just because, of course, there might be short-term adaptive behavior of firms that kind of buffers this, or operational risk management that leads to a smaller shock in financial terms. However, I think all of these results are indicative of distortions in supply chains caused by these climate shocks elsewhere. All right, I think there would be a little bit more to be said about the economic magnitude. Maybe happy to talk about that later if that's of interest. Otherwise, I would say I'll move on to this maybe most interesting part of the study. And that is the part where we focus on, okay, what happens? How do these firms respond? And is there any adjustment in supply chain networks? So I think it's really important to lay out here that we think about that in the context, or say backed by some conceptual framework that is largely developed by a paper by Kelly et al. In 2005. And why that is important is the following reasons. So first of all, we start from the intuition that customers aren't completely naive. Actually, it's really costly to pick up supply chain relationships, and often there are specific investments that have to be made. So that is not an easy decision to be made on the firm level. And we assume that customers have some information on the ex ante probability of climate shocks occurring at the supplier location, as well as some knowledge that a lot of these shocks is determined by a stochastic process. So what really matters for the choice of these relationships is actually the average exposure and not the realization of every single shock. Moreover, we assume that customers may trade off the exposure to climate shocks and other factors, such as the input costs at certain locations of suppliers in making these decisions. And what I mean by that is that we observe this correlation between the economic development of places and the extent to which they're hit really hardly by climate changes, or at least the projected change. And that leads to a situation where a place that is more risky in a developing country might still be attractive if that is reflected in the input costs, but in some sort of competitive framework, we would expect that every firm optimizes this decision and kind of trades off these two aspects. So in that scenario, I think it's really important to highlight that we would not expect that there should be any effects of short-term changes or short-term shocks in heat or floods on the continuation of supply chain relationships. Just because, again, there's an underlying stochastic process. In a sense, it would be really irrational to terminate relationships just for the short run changes around the mean exposure in a certain place. However, we would argue that if there has been an optimization in place that trades off the average exposure and the input cost of this specific supplier, then a permanent change and a shift in the distribution of these climate risks could render a previously optimal choice of a supplier suboptimal. To kind of say the same thing, we created this figure here. So maybe let me quickly show you how the figure connects with this intuition that I just explained. So if you look at that, what you see here is a supply chain relationship, a hypothetical example. And if there is a customer firm that is deciding to work with a certain supplier around T equaling 0 here, then we assume that this customer looks back in time and comes up with a historical estimate of the expected climate risk exposure in this place. So this is very consistent with these other studies on learning about climate change in the environmental economics literature. And then going into the relationship, we start off with a setting where we think that firms may do something that's very consistent with Bayesian updating and that they mainly learn from their experience. And then what I mean by that is essentially that going into the relationship in every period, the firm learns about signals in terms of the realized weather conditions, in terms of floods and heat waves, and can kind of compare the actual realized variation to what's happened in the past. And then we create an indicator or a running measure of what happens or when the point sets in where there's a deviation between this past expected exposure and actually realized exposure. And again, in line with this assumption about this optimization and trade-off of input cost and risk at a supplier location, we would assume that this is the thing that can trigger the disruption of supply chain relationships. So much about the empirical strategy and well, first of all, the intuition of the empirical strategy. The corresponding empirical strategy looks something like this. So we study the end of supply chain relationships. So in a panel, one in the last year of the relationship being active. And then we study what effect there is of this deviation between realized and expected climate shocks. Again, controlling for a lot of different trends. So for example, to pick up trade effects, we control for supplier country times customer country times time fixed effects. And data actually allows us to do that in terms of the variation that is available. And I think those controls are really important to give us comfort that what we see here is really about the climate conditions and not about potential confounding trade effects or treaties or something like that coming up. Another thing to be said is that we decided it would be convenient to start from this assumption that firms only learn from experience and only work with, so to say, this experience measure and a deviation of the realized climate from the expected climate, because this is fairly randomly distributed. And that's something that we, to some extent, verify. Again, probably would be helpful if I go into that after the talk, if there's interest in that. But just in terms of this short run deviation, this is fairly randomly distributed. And that's one thing also that makes learning about climate change really hard, just because often these short run trends and medium run trends can deviate from what's actually expected to change in a given place. All right, but with that, so that is the empirical setup, so to say, testing this relation between the variation, to what extent realized and expected exposure fall apart. And this is the corresponding result. So what we find is that indeed there's a strong increase in the likelihood of supply chain relations to end once there is a deviation between these two things. And that holds both for heat days and for flood days. And again, we kind of find it reassuring that in terms of significance, that's very much in line with also the differences we find in the magnitude of the shocks that are propagated in the supply chains related to heat and to flooding. We do lots of robustness tests for that. For example, we estimate these periods where the expected exposure is estimated for, I think, 5 different steps between 5 and 15 years. And moreover, we also work with different measures of exposure. So we look at the days of exposure as well as the shocks over time.
Sorry, Nora, you have 5 minutes.
Excellent, thank you. I think that will work out really well, actually. So there's one more finding after that. But so first of all, again, to zoom in on that. So the baseline result here is that there's an increase in the probability if climate risk exposure at the location of the supplier changes. Again, thinking a little bit about what that tells us about how firms learn about this. So first of all, this would be pretty much in line with the standard model of Bayesian updating, where firms primarily use their experience as well as a historically estimated prior. And in line with that, we also find that this effect increases with the size of the shock that we observe. So if we change this from an indicator variable to the actual size of the deviation, as well as when the signal is repeated, which in this construction of the measure doesn't happen extremely often. So I think on average, we find that firms experience this deviation twice over the relationship period. Okay, and then really importantly, this is something that I want to stress, again, linking to the conceptual framework underlying this whole estimation. So definitely we would not expect that there's any reaction to transitory shocks here, just because, again, we assume that firms are to some extent aware of this stochastic process and the transitory nature of these shocks. So in other words, that also gives us an opportunity to test to what extent firms really stick to this Bayesian framework here, and to what extent there might be some evidence for the availability or heuristic here. So just individually, if we regress just the occurrence of shocks on the probability of the supply chain to end, we also find a really small positive effect. However, that will be economically significant. And as soon as we, so to say, horse race these two different ways to think about it, so this deviation and expected and realized risk, as well as just the contemporary shocks, we find that also in terms of statistical power, the effect really seems to be driven by this deviation in experience and expectation that might render the previously optimal choice of a supplier suboptimal. All right, so this is our baseline result, but then again, and this goes a little bit into the new version of the paper, so to say, so I'll try to not venture off too far on that end just because this update has been really recent. So, but I think what's really interesting and what we hence also decided we wanted to show today is that we can now look into to what extent this learning from the short-term experience makes sense if we combine this with data on the projections of temperature changes in certain places. And how we do that here is we use this models from the CMIP5 experiment that's tied to the last IPCC report. And we focus on the business as usual estimate just because we kind of need the upper bound of the effect. So assuming that firms might think, okay, or no, assuming just a scenario where there would be no policy intervention at all. And then what we can do is, since there's availability of this data on a daily level, so daily simulations, by European Climate Institute, we essentially come up with a measure of this projection that exactly corresponds to how we measure these shocks in terms of heat days during a financial quarter, in terms of the projection, and compare these two. And the first way how we do that is the following, because essentially our ambition here is to stay out of exactly thinking about how firms may use these different scenarios out there, what their assumptions are about policy stringency, what their assumptions are about the physical processes, so to say, they would be tied to changes in emissions. And we set this up in the following way. What you see here in this table is, again, a similar regression of the deviation of realized and expected heat days on the probability of a supply chain to end. But then if you look at the part that I'm circling here right now, you see the results for the full sample. And if you move to the right on the slide, you see this same result for the part of the sample where actually these climate models project no significant change in the number of days per year over 30 degrees Celsius. And yet we find that this effect is actually slightly stronger in magnitude, but also very similar in terms of direction and significance. And we take that as first evidence that it might be the case that firms actually update based on just their experience compared to a historical prior, and leave this information on actually projected change on the table. With that, let me jump to the next piece of evidence, so to say, on how this process works on the firm level. So far, we estimated just the probability of supply chain relationships to end. What we do next is to dive into how these initial suppliers are replaced. And again, the data makes this possible. So we can identify both the terminated supplier as well as suppliers that are in the same 4-digit SIC industry and where the relationship starts within 1 year of the termination of the initial supplier, so that we kind of suppose that those two actions might have something to do with each other. And most likely a large share of the sample is the actual replacement. And then what we want to see, just to get more insight into whether there's any climate awareness in play here, or how firms think they manage this risk once there's a deviation of the experience from the expectation, is the following. So we want to avoid that our results are in any way confounded by potential trends in climate. And that could easily be the case as soon as we look into one supplier that has been in place earlier and compare it to a supplier that has been in operations with a customer firm later on. So how we do that is that we're very strict about comparing suppliers over the same time periods. So this is a hypothetical example, but just here we would compare the replaced supplier to the actual replacement during the relationship as well as during the new relationship. And what we find if we look into this comparison, and again, linking this to this measure of whether actually there might be an incidence that could have triggered such a supply chain disruption induced by climate shocks and change in climate risk, we study whether the probability of a decrease, so the new supplier being less exposed than the old supplier, is driven by this condition that the termination might have been climate risk change induced. And again, we control for a really large set of fixed effects here, again, to address this potential risk that this is not purely random, this variation, and that there might be confounding effects from trade treaties and trade in general. And probably I'm slowly running out of time, but I think this is also the last result. So what we do find is that during the relationship, it seems like the new pick is actually a very good pick, just because the decrease becomes more likely, so that the new supplier is actually less exposed. However, again, in line with this fact that maybe firms are not really forward-looking in doing this, once we look into the relation between the two after the initial relationship, we find that there's no significant difference. And with that, I'll conclude. So in a nutshell, again, we find some evidence, maybe the upper bound in terms of the financial outcome that we see of potential distortions in supply chains. We find that climate shocks decrease both suppliers and customer revenue and operating income over assets. And that connects to both the propagation of shocks in supply chains, but also as an indication that is important for finance in general, that maybe these shocks are not as idiosyncratic as you could think if you don't think about the trends of climate change in the first place, just because there's a propagation of climate-related shocks in these firm networks. And moreover, we find that customers are more likely to replace suppliers when this realized climate exposure deviates from the expected shocks. Again, highlighting here that this is very different from thinking about just the effect of transitory shocks on the continuation of supply chain relationships. And interestingly, it seems like forward-looking information might not be driving these decisions. And that, again, is in line with the literature in environmental econ on learning that stresses difficulties in, so to say, combining both the experience and the forward-looking information. Thanks a lot for your attention, and we're looking forward to your questions and comments.
All right, thank you, Nora, for the presentation and for joining us at a very early hour from LA. The discussant is John Hassler from IES at Stockholm University. John, you have 15 minutes.
Thank you very much. Thank you very much for allowing me to discuss these interesting papers. So I'm going to start with just a very short recapitulation of the contents of the papers. So Adrian's paper is, both papers are actually about supplier-customer relationships. And this is an interesting topic that I haven't read much about before. So I like that a lot. So Adrian's paper is about the consequences of weather events on supplier-customer relationships in the US. And they get a couple of interesting findings. In particular, what they find is that an increase in the average temperature of a particular year relative to the long run average reduces supplier sales significantly, statistically and economically. So think of this as if a particular year is hot relative to the average in that location, then sales goes down. They do not find any effects on supplier-customer link breaking probabilities, and that's a little bit of a contrast to Nora's paper. But of course, it's different data, so one doesn't really need to think that they should get the same results there. Since Nora's paper is about kind of international supplier customer links, so this Adrian's is on the US. What Adrian also finds with his colleagues is that you get stronger effects on sales in labor-intensive and small firms, and also firms that we think might be financially constrained. So that's also an interesting finding. And they also find that the effects are larger in sectors where we seem to have some reason to believe that they are more heat sensitive. And there are some papers studying this previously. And as Adrian pointed out, it kind of seems to have to do with whether a substantial part of production is taking place outdoors or not. So that seems to be kind of reasonable for agriculture, paper and forest maybe, but maybe some of these industries are kind of, it's a little bit hard to understand from the paper why they should be heat sensitive. So that's one point. Okay, so that's a very short description of Adrian's paper. Now let's go to Nora's. So as I said, it's also here weather events. They are defined a little bit differently, as you heard. It's not kind of the average temperature. First, it's both about heat and about flooding, and it's more kind of an event here is defined as some extreme realization of temperature or flooding. And what they find is that both these floods and heat waves decrease suppliers and also customers' revenues and profits. And here they find that to be statistically and economically significant. they do not find directly that floods and heat waves to suppliers, if you just put them into the regression and try to explain where their links between supplier and the customers are breaking down, if you just put in these things, these events in the regression, there is not much of an effect. But as Nora pointed out, if the number of shocks, floods or heat days in a year is higher than the historic average for that location, then the share of links breaking up increases substantially. So it's kind of this deviation from what you expect, as Nora pointed out. Another, I think, very interesting point is that when a supplier is replaced, and arguably for having then seen a lot of these weather-related shocks, then it seems like the replacing the supplier that replaced the old one is less exposed to these kinds of weather shocks. Okay, so the statistical analysis and the data is interesting and surely competently done. So I'm not going to spend too much on that. I just want to say that I think it's very important to do these kinds of studies. We certainly need to know much more about the costs of climate change. I do the macroeconomics of climate change, and we really need these kinds of inputs. But I'm a little bit, questioning whether all the results really are about the cost of climate change. First, a simple thing is, of course, to say that what we need to know is kind of aggregate costs. If we are talking about the inputs into discussions about what kind of policy we need to aggregate. That maybe it's kind of the job of us macroeconomists, but nevertheless, I think that's something that should be kind of maybe thought of in papers like this. In any case, this aggregation should certainly be kind of based on micro studies like this, for sure. When you do these kind of things, it's also, I think, interesting to try to be to say something about quantities. Are these risks large relative to other kinds of risks that firms faces, and in particular when we talk about climate change, risks that kind of develop over a very long time, and to me my gut feeling is that these are not large risks, but I think that's important actually if you want to contribute to the climate change literature, to take that discussion seriously. Are these things large or are they not? It's also that I think that we kind of need to think a lot about what kind of questions can be answered with data like this. And let me just take maybe a simple point here about that, and that is that both papers kind of use, in a sense, similar empirical strategies, but one talks about weather shocks and the other about climate shocks. I think you're actually talking about the same thing, and it's and perhaps it's obvious, but weather and climate are two very different things, and I think that needs to be kind of thought of more in studies like these. So weather is kind of an event, right? But climate is kind of the distribution of these kinds of events. So mean, standard deviation, maximum temperature, wind speed, and precipitation. And when we talk about climate change, we talk about changes in these characteristics of the distribution of the weather events. And it's a very hard task to think about how we can identify effects of climate change from looking at weather events, and it's a difficult issue. But I urge everyone to take that serious and at least think about it, because I've seen papers where this is not taken seriously at all, and the effects of weather events are just extrapolated for decades into the future. And to me, that makes absolutely no sense at all. So always make a clear distinction between weather events and climate change. And this is because we have all the reasons in the world to believe that there are differences in the way weather affects payoffs and behavior, and the way climate change affects payoffs and behavior. We have, I mean, for example, we know that deviations in temperature from kind of the average affects humans' health, but kind of what's the optimal temperature from a health perspective seems to vary a lot across different locations. So this, I think, is an important point. And as I said, this is difficult, but nevertheless, it's necessary. So I'm going to end with just some kind of very kind of rudimentary or simple thoughts I had about how informative the weather shocks that you use are about what we're interested in, namely climate change, the effects of climate change. So in Adrian's paper, what you use there is that you say that sales falls what seemingly linearly in temperature deviations from the normal in that region. But what climate change is going to do is that it changes what's normal. So it's so here this issue comes up, and it's not entirely clear to me why the results should say something about how firms, for example, profits and sales change when the normal changes. By construction, in a sense, the effects of the normality are taken out. And another thing is that the finding that the effects are linear also implies that if we are worried about increases in the variance of weather, I'm not sure actually that there is much of evidence that the yearly variation in temperature is going to be larger in the future, but perhaps. But nevertheless, the linearity here implies that the standard deviation is not going to change average sales. You need some non-linearity for that to matter. But here your extreme event analysis, of course, provides important evidence. So the extreme event analysis, I think, clearly could provide evidence about, it could kind of identify the effects of climate change, while the others maybe not. At least I think you need to kind of push that harder. Nora, what you find, an important finding in your paper is that if you have more than the expected number of weather shocks, then you get effects. And in particular for the breaking up of the links. But here again, kind of you take away the effects of the changes in the expected number of shocks. So here it's also not, to me, obvious that this really identifies the effects of climate change. On the other hand, this thing that you stressed in the end, that when firms are changing supplier, and in particular, if you can argue that those changes are due to there having been more than the expected number of weather shocks in the past, these new replacing firms are located in areas where you have where you are likely to have fewer weather shocks in the future. That strategy, I think, could potentially be valuable if you want to identify the effects of climate change. Of course, the problem is that there might be other trends, and you talked a bit about it, that confound these findings. In Okay, so my conclusion is that these are quite interesting and very competently executed papers, but this issue about how should we identify the effects of climate change as opposed to weather events, it would be very useful if micro people like you think about that and provide some insight to us as macroeconomists. Okay, thank you.